All right, good day everyone. Today our lesson here is going to be on Newton's third law, right? We want to understand it a little bit more on how we can, you know, interact with Newton's third law. So we know that Newton has many laws, but as it relates to Newton's laws of motion, we are focusing on his first, second, and third law. In previous lesson, we have talked about his second law, where it speaks to the rate of change of momentum, right? And that is how we end up getting what we call mass times acceleration. Force is equal to mass times acceleration. But we're not focused on that for that part in this particular lesson. What we're going to focus on is his third law. And on the screen here, you can see that it says that Newton's third law speaks to if an object A, any object, so to speak. So if object A exerts a force on another object, and in this case we'll call that object B, then B will exert an equal and opposite force on object A. So that's what Newton's third law is from a worded standpoint. Now, a lot of things observe this type of law in nature, right? So, simply if you have a cup sitting on a table, right? The cup itself has mass, and for that reason, it's going to have a weight. And weight is a force that acts directly downwards. So we're expecting that the cup is going to exert a force down on the table. Now, the tendency is for the table to exert an equal and opposite force to that object. So that's just simply Newton's third law. And let's look at this example of having a book sitting on a table, right? Now, we have to be mindful whenever we're dealing with Newton's third law. It can only involve two objects, meaning that if I were to put another object on top of the book, right, then it would not work, right? You can't apply Newton's. So if I had a cup right here, right, a cup of water, then this involves three objects and you are having more forces coming into play here, so it wouldn't work. So it only works when you have two objects being involved, right? Just the table and the book. So what we're saying now is that the book is going to exert a force going downwards. Now, whenever we're talking about downwards, we generally associate downwards with negative. Follow me? And because the book is exerting a force downwards, right? Let me just erase this cup right here. So seeing that the book is exerting a force downwards, we're saying based on Newton's third law that the second object in this case, which is the table, will exert an equal and opposite force. Now, if you exert an equal and opposite force going upwards like this, by way of vector addition and vector subtraction and so forth, we can clearly see that the resultant would basically equal to 0. So if you have 10 newtons going up and you have 10 newtons going down, we automatically see that these two are going to cancel. And as a result of this, we can simply say that the book is at rest. So whenever the upward force is equal to the downward force, there is no movement, right? There is no overall movement of the object. And what this also tells us that the object is not accelerating, right? Now, it says by Newton's second law, the vector sum of W and Fn. By the way, I should let you know that Fn speaks to what we call the normal reaction force. And that is usually the force that is exerted from a surface area. So any object that is sitting on something, right? The object that it is sitting on, in this case the table will exert a normal reaction force. Good. And that force is perpendicular to the surface, right? Perpendicular to the surface. Now, because the object here is not accelerating, right? By Newton's second law, we know that Newton's second law, let me just write it right here. Newton's second law is equal to net force equal to mass times acceleration. Seeing that we're saying that upward force is equal to downward force, it therefore tells us that the thing has no net force. Well, basically, right? Or what we're saying is that there's no acceleration. The book is just sitting on the surface. So if the book is sitting on the surface, then it means that there's no acceleration, right? So A is equal to 0. So for that reason, our net force is equal to mass multiplied by 0, and any number multiplied by 0 is equal to 0. Now, as it relates to our net force, that's a very key part now, right? Because what you would see is what we have talked about just a while ago. As regards to the net force, all we're simply doing is adding the upward force, right? And adding the downward force. This is now when the direction, meaning the positive and negative, comes into play. Remember, we said that going up is positive, going down is negative. So it therefore tells us whenever you're talking about net force, is just the resultant forces, so to speak. Good. So if we were to add these, what we're saying is Fn, which is the upward force, so that's positive, plus our downward force, which is negative W, all of this is equal to 0. So it is as a result of Newton's second law why we can now say that upward force is equal to downward force. Because from this operation we can simply we can do a transposition to make Fn equal to W. And that's how, by the way, yes, let me just correct myself. Looking at this right here, I shouldn't have incorporated the negative as yet, right? I won't incorporate the negative at this point. So let me just erase that negative. Yes, we know that going down is negative, but we're not interested in that. What we're interested in is adding the forces, adding the both forces. And by way of transposition, right, we get Fn is equal to negative W. Now the negative is just to tell us the direction of the weight, right? And we know that the weight is going down. All right. So that just balance out all of what what Newton's third law is really saying. It is saying that both forces are equal, but they are opposite. If they are opposite, it means that one is going positive, one is going negative. All right. It says now that this vector equation shows us that normal contact force is equal and opposite to the weight. Similar to what I said. All right. Yeah, it's important to note that it says no, but are these action or reaction forces of Newton's third law? Now, I would basically say that it's a reaction force, right? Because it is as a result, because the weight is going down on the table, right? There's a reaction taking place. So the normal reaction force is reacting to the weight that is acting down on the surface. All right, now let's move on a little bit. We talked about Newton's third law, but yes, we're still going to apply it a little bit here, right? In some regards, not quite, but yeah. Frictional forces. When we talk about forces, we talk about a push or a pull. Now, there are different types of forces, right? In some event, we will come across these two types of frictional forces, right? And we know when we talk about friction is an opposing force relative to motion. So if you're moving something to the right, then there's an opposing force that is basically stopping, wanting to resist or to oppose the applied force, or to resist the motion of the object. Good. Now, since the object is, let's look at this. So generally speaking, if you have something sitting on a surface, right? Now, there are times when you will apply a force to that object and you realize that the object does not move, right? It is just as a result of the fact that there is what we call static friction, right? So static friction is associated, it's a friction that even though there is an applied force, it's just telling us that there is not enough applied force to overcome that type of friction, right? And it tells us that this is the friction that keeps something from not being pushed. You understand? So imagine you put a box on the floor with a stack of books. You go ahead and you now try to push it. Static friction will stop you from, or will oppose the applied force. So imagine if you have this scenario right here where there's some applied force. We know that because the object is sitting on the surface, right? We know that Newton's third law would come into play here to say that equal and opposite forces being observed right here. Normal reaction force and the force of gravity, which is the same thing as the weight, and we have one force going in that direction and one force going in this direction. Applied force in this direction, frictional force in that direction. Now, as you know, let's look at another type of friction. So we have looked at what we call static friction, and we said that is that friction that pretty much stops something from being pushed. Now, what if you were to apply more force to the box of books that you would have stacked on the floor? If you apply more force to that particular box of books, what you would realize is that there will be a point where the box will start to move. And all this is telling us is that you would have overcome the static frictional force, but yes, the box is still moving on the surface. So by moving on the surface, we now have what we call kinetic friction. And it is a force that resists the relative motion of the surface, right, once they are in motion. So once the box is being pushed, follow me, you will realize that there is still a type of friction, but this one is now related to what we call kinetic friction. And so, but we no longer would have static friction, right? Once it is in motion, we now have kinetic. If the thing is not in motion, then we have static. All right. So that's something that we have to point out, and what that you have to remember, that there are two types of frictional forces. Static has to do when the object is sitting on the surface. It stops it from moving. As you apply more force, then you overcome the static friction, the static force, right? And you now have what we call kinetic friction. And this is just as a result of the fact that the object is still being in contact with some type of surface. And so once it's in contact with some type of surface and it is in motion, then we have what we call kinetic friction. Now, let me just explain a little bit more, right? You will hear us talking about what we call limiting friction, right? Now, the very moment, because remember now, when the box is sitting on the surface, right, there is a time, or not a time, but there is a particular amount of applied force that is required for the box to start moving. The very moment the object starts to move, it means that we have now reached the maximum kinetic frictional force, right, between the surface. Once you have reached that amount, we basically call it the limiting friction, right? So that's a point where there is no longer any static frictional force, and that is when we now have kinetic friction coming into play, right? There's an important thing to note is that, and you will see it from a graph, that while the static friction force will vary with the applied force, right? When we look, let's look at this graph right here. So this graph is a friction versus applied force. Let's picture the box again. The box sitting on the surface. Now, if we were to apply 10 newtons of force, right, what we would realize is that there will also be 10 newtons of resisting force, which is what we call the static friction force at that point, resisting the movement of the box. So we're seeing at this point that there is some type of relationship going on here, because if I'm increasing my applied force and my static force is also increasing, then that just shows us that, you know, the box really won't move up to a point. You understand? But as we apply more force, like you know applying more force over time, we then realize that the static friction can no longer be there. It's going to reach a point, a threshold point. You know, by threshold, we mean that, you know, it can't go no further. You understand? So once it reaches that point, we know the box will now be able to move. Follow me? And afterwards, because if you're looking at the graph, you realize that this proportional relationship taking place here, then there's a drop in the graph. So the very moment we have overcome the limiting friction, we realize that the graph decreases, and then it has a steady graph going along the x-axis. This part of the graph will explain the kinetic friction. If you go back here on this slide, it tells us that the kinetic friction does not vary with applied force, and it says that it remains rather, fairly constant, so to speak, right? So that's how the two frictional forces operate. Good. Now, as regards to these two forces, right, each surface, each material that we have has certain ability to resist the movement of so certain materials, right, if you have a rocky surface and you have a smooth surface, the rocky surface would more likely have more resistive ability, more resistive component to it. You understand? Seeing that we're talking about friction has to do with resisting movement. Now, there is what we call the coefficient of friction, right? And all the coefficient speaks to is the amount to which the surface can restrict motion or so forth. Right? Now, each frictional forces, so we know we have static friction force and we have kinetic friction force. Each forces has its own coefficient of friction. Now, if we're thinking about our static force, which is the same thing as our what do you call it, the limiting friction. The limiting friction has its own coefficient value, and the coefficient, the symbol for the coefficient is mu, right? But there is something spectacular about the frictional forces that we are talking about. There's a relationship between the frictional force and the normal contact force. So if you go back here, or let's look back at a diagram. Whenever we have an object sitting on a surface, we can draw the forces that are acting on the system. There is the downward force, weight. There is the upward force, which is equal and opposite to the downward force. That is what we call our normal reaction force. We have our applied force, maybe going in that direction, and then we have our frictional force going in the opposite direction. Now, by way of doing some type of experiments, we have come to a point where we realize that there is a proportional relationship between the we'll call it the normal reaction force and the frictional forces, so to speak. It makes sense, guys. Let me show you why it makes sense. Now, if you have more weight acting down on the surface, it means you're going to have more normal reaction force. Having more weight going down on the surface means that you have more frictional force, right? Which is stopping the movement of the object, if you follow me, right? Think about it. So the more books you have in the box, let's imagine that this is a box sitting on the surface. The more book you have in it, it's the more weight you will have, therefore it's the more normal reaction force that you will have, and it's going to be much harder for you to move it. So it therefore tells us that with more weight, it requires more applied force, and by requiring more applied force, it means that we have a much larger limiting friction, or a much larger static friction force. So we have seen that there's a relationship taking place here, and it's a directly proportional relationship. So if we were to plot a graph, right, let's imagine that we're plotting a graph of normal reaction force versus kinetic frictional force, not kinetic but static frictional or limiting frictional force. You would have a graph looking like this, right? You should have a graph looking like that. Let me just check it here. Give me a second. Well, not like this. Let's put F, the limiting friction on this side, right? And then let's put Fn, which is the normal reaction force. Because what you would realize is that if we transpose the equation, right? Because if we're seeing that there's a directly proportional relationship going on here between the frictional force and the normal reaction force, if we were to plot a graph, right, whatsoever the gradient is, that gradient should tell us the value of mu, right? So this is probably a lab that we might do as well, trying to find the coefficient of friction, so to speak, right? And this varies, as we said, with the type of surface that we're using. Now, so here are two equations that we have to pay attention to, right? These are two equations that we will always come across whenever we're dealing with stuff that has any type of friction. So for an object that is not moving, right, then this is the one that applies to say that the limiting friction, which is the same thing as a static friction, is equal to a constant, which is mu s, and the s here stands for the static frictional force. So the coefficient of static frictional force multiplied by the normal reaction force will tell us what the limiting friction is, right? And similarly, if the object is in motion, we also see that there's a directly proportional relationship with the kinetic friction force and the normal reaction force. However, the constant here is going to be the coefficient of kinetic friction force, frictional force. All right? Yeah. So here is what we are saying here, that mu s is what we call the static frictional force. I think this should have been mu k right here, right? Yeah. Okay. So these are stuff that we're going to apply. Guys, remember that you will get questions that it might not tell you what the normal reaction force is. But the normal reaction force is automatically equal to the downward force, right? And we're going to look at different scenarios, right, where you will have to find the normal reaction force. So let's look at an example here, right? it says to us that a crate or a 5 kilogram crate is pulled along a horizontal floor with a 300 newtons horizontal force as seen in the figure below. It says determine the acceleration of the box if the coefficient of kinetic friction between the crate and the floor is 0.6. Now just be mindful that the coefficient of kinetic friction does not have a unit, it's just a constant. Alright, this is your free body diagram. We have looked at how to draw free body diagrams. Quite often you will be required to draw free body diagrams. Now we can establish something here. Now because the object is being pulled towards the horizontal, right, there is no acceleration along the vertical. Following? So because the object is being pulled to this end, there is no acceleration along the vertical. So by way of looking at Newton's second law, we can simply equate both of these things, right, and say that Fn minus mg is equal to 0. So therefore upward force is equal to downward force in terms of their magnitude, but we know that they're going in opposite direction. So we know what the normal reaction force is equal to. Now it says now, if we want to find the acceleration along the horizontal, we therefore have to look at the net forces acting along the horizontal. So one of the forces acting on the horizontal is the applied force, and this is going to the right. Then we know that the frictional force would be in the opposite direction. So our Fk, which we're going to call that our kinetic frictional force, will be going to the left. So if we're trying to find the net force, we would obviously, whenever we're summing up these two things, we normally put the positive one first. Remember, going to the right means positive, going to the left means negative, right? By way of looking at your Cartesian planes. So if we were to divide this as a Cartesian plane, then going to the right is positive, going to the left is negative. So if we are trying to find the net force, we're saying that the applied force minus the frictional force is equal to the mass times acceleration, because the object is now accelerating along the horizontal. Now, because there is a relationship between the normal reaction force and the kinetic frictional force, in which we know that Fk is equal to mu k times Fn. Because we know this relationship, we can find what the kinetic frictional force is. Remember though, the question did not give us what the kinetic frictional force is. It did not give us that. So by way of calculation, we would have multiplied 0.6 times the normal reaction force, which is equal to the weight of the object, which is 490 newtons. And if we go ahead and multiply these two numbers, we get a value of 294 newtons. So that's the kinetic frictional force. As you can see, it's a very high kinetic frictional force, right? It's very high. So we can know that the box is not going to accelerate a whole lot, or the crate in this case. So by way of subtracting the applied force, which was 300, minus the kinetic frictional force, we get some type of number. I don't know what that is, but yeah, I think it's 6. Yeah, it's 6 right here. If you follow on this screen, you realize it's 6. So yeah, it's 6. So by way of just doing a simple mathematics here, right? We know the weight, we know the mass of the crate, which is 50 kilograms. So by way of dividing 6 by 50, it gives us a value of 0.16 meters per second, and that tells us the acceleration. All right. Now you might be wondering, how does Newton's third law come into play? Yes, Newton's third law came into play a while ago when we looked at the vertical axis of the box, the force acting along the vertical. So once the object is sitting on the surface, right, then there's going to be force acting down, and as a result of that, a reaction force, which is the normal reaction force, right, which acts from the surface directly upwards. Right? Now, from time to time, you will get different scenarios, right, where you will need to find either the coefficient of static friction. So if we were to consider somebody, or this young lady right here, sitting on a seesaw, all right, not a seesaw, my bad, a slide, you know, those regular slides that in the kindergarten parks, right? Now, having a girl sitting on this thing here, we realize that she's not moving, right? So it therefore tells us that there is some type of the static frictional force in this case is much larger, or we would say, yeah, it's much larger than the applied force. Now, because we're looking at an inclined plane, guys, right, we know that the weight is a force that always acts directly downwards from the object. Now, this is what we're doing. We know how to resolve these forces already, right? But let's just go back through it. Now, quite often, the force that we would need to resolve is mg, which is the weight. We need to resolve the weight because it is the only force that is not acting perpendicular to the surface right here that the person is sitting on, right? So for that reason, right, we have to resolve it into its horizontal and vertical components. Right? So by way of resolving it, we know if we were to resolve this weight component, due to the fact that there is an angle between the weight component and between the weight and the vertical component of the weight, we therefore say that this component is equal to mg cos theta. Now, by way of resolving this force again, we can now get the horizontal component of it, and that is equal to mg sine theta. So we can see a better relationship of the forces acting here, where we can see that the normal reaction force is equal to mg cos theta, because it is equal and opposite. Now we can also see that the limiting frictional force is equal to mg, well, not necessarily equal, you know, I don't want to say that, right? Yeah, let's not say it. Yeah, we can say that. Yeah, they are equal because the object is not moving, right? So, well, not the object, the girl here is not moving, so we can say that, and you can follow from here, right? So because there's no acceleration along the incline, this is what our net force would generally be, right? mg sine theta minus the limiting frictional force is equal to mass times acceleration, but acceleration is equal to 0. So for that reason, we get this right here to say that mg sine theta is equal to the limiting friction. Now, along the perpendicular axis, right, we can see that the normal reaction force, there's no acceleration along the perpendicular axis or along the vertical, right? So we can equate this to say that mg cos theta is equal to Fn. Now, by way of dividing both of these equations, right, whenever we have these two ratios, well, not ratios, but whenever we have these two trigonometry trig ratios, I should say, whenever we have these trig functions, rather, if we have sine divided by cosine, this is the same thing as saying tan theta. So always remember that if you see something to say sine divided by cos, it is basically telling us that it results into what we call tan theta. And you can find these functions on your calculator. So by way of doing this, right, we would be basically left with, we can cancel out the mg's, right? Those are gone, all right, and then we are left with tan theta equal to limiting frictional force divided by Fn. Now, if we look at the relationship between limiting friction and the normal reaction force, limiting friction is equal to mu of s times Fn. So by way of just transposing to make mu s becomes the subject, we get that tan theta is equal to mu of s. So generally speaking, guys, what we're trying to find here is what is the coefficient of the static friction, right? And this is really as a result of what the incline is made up of. Now, there's something important that we should talk about, and it is the fact that what will affect the what affects the movement of this young girl down by on the incline is by virtue of the angle, right? So because as you can see right here, we have tan theta is equal to mu s. So if we increase theta, right, by increasing theta, we're impacting the coefficient of friction, of static friction. So this just shows us that if we were to bring the incline up in the air some more, where it has a much larger angle, then this would affect the ability of the seesaw to know, restrict the friction. The much higher the mu is, it tells us whether, let me just check something here, right? Yeah, so it says the larger the coefficient, the greater the frictional force between the surface. Okay, yeah, so the larger the angle is, it's the more frictional force that we would ultimately have, our larger coefficient of static friction that we would have, right? So the angle can really tell us, you know, how much of a frictional force, or it will ultimately affect the movement of the system. All right, let's look at this question here. It's, you know, let's tie in what we have learned, so to speak. So it says that a 1.5 kilogram box is given an initial velocity of 2 meters per second up a plane, which is an incline, from the bottom of the plane. The plane is inclined at 30 degrees to the horizontal. The coefficient of kinetic friction between the box and the plane is 0.44. It says determine the acceleration as it travels up the plane, and it tells us now that they want us to find the distance at which the box travel up the plane before coming to a stop. All right, so this is our incline. It tells us that the incline makes an angle of 30 degrees to the horizontal. It tells us that the box has a mass of 1.5 kilograms. Now it wants us to find the acceleration. So clearly we know that we know that there is going to be so the box is moving up the incline. Follow me? Let's just see if we can kind of draw in the different forces that will act on the box. One force that we know is going to be the normal reaction force, and that is perpendicular to the horizon, to the plane, to the surface. So that's where our normal reaction force would be. Now we know that the weight force is a force that is acting directly downwards from the object. All right, so this is our weight. Now there are a few things that we need to do here, right? We need to resolve the weight component. We need to resolve the weight component. Now let's just put in where the vertical component of the weight is going to be. Now remember that we said that between this vector W and this one right here, the angle is 30 degrees. So it mimics whatsoever the angle is in between the incline and the horizontal. So by way of thinking about what we call it now, by way of thinking about the right angle triangle, right? We basically know that this is going to equal to W cos theta, which is ultimately equal to W cos 30 degrees. Now because we are splitting the weight into its horizontal and its vertical components, right, we need to also put in the horizontal component. Now because the object is moving upwards, right, we can say that the weight, the horizontal component of the weight is equal to this vector that is going upwards, and this is equal to W sine 30. Now because the object is moving upwards, then we expect that the limiting friction, right? The limiting friction is an opposing force. Good. All right, I'm going to correct myself a little bit here. I don't think I want to consider the weight force acting upwards. So let's just erase that a little bit. So let's not say that the weight force is acting upwards. It really, that component is not really acting upwards. It really is supposed to be acting downwards. So this is what we're going to have. This is what we're going to have. So the weight component, right, of the horizontal is going to be W sine 30. Now there's another force that is acting in this direction as well. Now remember that the box is going up, right? So if it's going up in the air like this, then it means that there's going to be some limiting frictional force, which is going to be our kinetic frictional force that is acting downwards. Good. Now we want to find the acceleration. So it therefore tells us that we have to, find the net force acting along the horizontal. So these are all the forces that are acting on the horizontal, and all of these forces are going in the same direction. So by finding the net force according to Newton's second law, right, we basically have Fk plus W sine 30 is equal to mass times acceleration. The mass is 1.5 times the acceleration. Now, in order for us to find Fk is equal to mu k times Fn. Remember that relationship between the frictional forces and the normal reaction force. So if I know mu k, which is 0.44, and I know the normal reaction force, which is equal to the downward force, in this case the downward force is going to be W cos theta. So Fn is equal to W cos 30. We can find the weight. The weight is equal to m times g. So 1.5 times 9.8 will give us, that gives us 14.5. So our normal reaction force is going to be 14.7 rather. 14.7 newtons times cos 30. Because remember now, we said that our normal reaction force is a force that is equal and opposite to the downward force. So that force that we're talking about it has to be opposite to the normal reaction force. So if the normal reaction force is on this side, then the force that is opposite to it is going to be W cos 30. So having said that, we can find what the normal reaction force is. So 14.7 times cos of 30, that supposed to give us 12.5 times the 0.44. So let me just fix this. 12.7 times 0.44. That tells us that mu k is equal to 5.6 newtons. So now that we know this, we can put in that value. 5.6 newtons plus W sine 30. We know what W is. W is 14.7 times sine 30. That gives us 7.35. 35 is equal to 1.5 times A, which is the area, not area, my bad, which is the acceleration, dividing both sides by 1.5. So let's just find the sum in the numerator on this side. So 1.6 plus 7.35, that gives us 12.95, dividing this by the 1.5. So we get now that the acceleration A is equal to 8.63, or we can just leave it as 8.6 meters per second square. All right, that is the acceleration of the object. Follow me? Yes. So that's the acceleration. Now we have to take this now, the other part of the question. So let's just recap what we have done. So what we tried to do a while ago was to find the acceleration. Good. And in order for us to do that, we have to incorporate Newton's second law. And we went ahead and realized we had to resolve the weight force into its components. So by resolving the weight is a vector that is acting downwards. So as a result of that, we get its horizontal component, right? And we get its vertical component. Good. And we just go ahead and put things together. So if we look at on the horizontal aspect of the incline, the two forces are acting downwards. So by way of just adding up those, we can get the net force that is acting along the horizontal. And now we can see that is equal to mass times acceleration. I will just go ahead and just work it from there. We had to find what the kinetic frictional force is, and in order for us to do that, we had to multiply mu k times the normal reaction force. Now the question also wants us to find the distance the box traveled, right, before it come to a stop. Now we have to treat this question as such that we know that when an object is coming to rest, right? So let's imagine that this is where the object stops. Cool. We can find that distance just before it stops by way of just treating that the box is actually at the position where it is stopping, so to speak, or just before it stops. You know, just before it stops means it's the same thing as saying the distance that it actually traveled. All right. So we need to know the time. All right. We need to know how long did it take for the box to travel from the beginning of the incline to where it stopped. And in order for us to do that, we have to use this equation that says V is equal to U plus AT. Follow me? Now, when the object is coming to a stopping point, the velocity is going to equal to, or we say the final velocity is equal to 0. Now, the question told us that the box had an initial velocity of 2 meters per second. So 2 plus the acceleration of the box, which is 8.63 times the time, right? I now can do a little bit of what I call it now, cross multiplication, right? We're gonna get a negative time, but we can just ignore the negative, right? We definitely can ignore the negative for this scenario. We could have used another equation, well, not another equation, but this is the more appropriate equation for us to use. So we'll get negative 2 equal to 8.63 times t, good, by way of just cross multiplying again, or not cross multiplying but dividing throughout, we get that negative 2 divided by 8.63 is equal to t. So let's try that in our calculators. As we're ignoring that negative, so 2 divided by 8.63, that gives us a time of 0.23 seconds. Now that we know the time 0.23 seconds, and we also need to know the acceleration. Acceleration is 8.63 meters per second. We know the initial velocity u was 2. Alright, now in order for us to find that distance, we have to use this equation to say that s, which speaks to displacement, is equal to ut, right, plus a half at squared. Right, let me check something. Here's another equation that says that v squared is equal to u squared plus 2as. So I think this equation could have used this equation already, you know, to find the answer. So let's consider this. We know that just before the object reaches, or when it reaches the point where it stops, velocity is equal to 0. We know the initial velocity in this case is equal to 2. So 2 squared is equal to not equal, but plus 2 times the acceleration, which is 8.63 times s. S is that distance that we're trying to find. So 2 squared is equal to 4, right? Minus so no, let me just not do that. So 0 is equal to 4 plus, let's work this out, so 2 times 8.63, that gives us 17.226 times s. So that if I bring the 4 across the equal sign, it becomes negative, plus 17.26 s, which is the displacement, that distance that we're trying to find. If I go ahead and divide through by 17.26, good. So 4 divided by 17.26, I get that the displacement is equal to 0.23 meters. So that is our displacement. That's how far the thing actually traveled. Alright, that's how far it actually traveled. Yeah. So this is what you would do to find the answer here. Alright, I think that completes this aspect of the lesson. Alright.